Hi, my name is Rohan Gupta, and today me and my friends are going to talk about computational fluid dynamics. And let me introduce ourselves real quick. So, starting from myself, Rohan Gupta, then Rohan Kumar, Rohan Rana, Rohan Sharma, Rohan Singh, Rohin Verma. Nowadays, CFD has become so easy to use that people use it without knowing the basics of it. So, today we are going to discuss some very basic concepts of CFD so that you can create better simulations for yourself. But before we actually dive into CFD, we must know what fluid dynamics really is. Fluid dynamics is study of flow or behavior of a fluid, and a fluid can be either a gas or a liquid. It can be applied in almost every scenario in our daily life, be it you drinking your coffee or driving your car. People have been studying fluid dynamics from centuries, and the past studies were either experimental or analytical. Experiments are fine and sometimes a lot of fun to do as well, but there are cases when actual simulations can't be performed, and for the experimentation, the analytical methods can get really difficult. In those cases, we require computer based simulations. Now, let's make it a little more technical. Now, let's have a look at the differential equations that govern the flow of the fluids. And after that, we'll look up why it's impossible to solve them directly and how we can convert them into simpler forms for the computers to solve them. These equations are based on the fundamental principles such as conservation of mass, conservation of momentum, and conservation of energy. To understand these situations better, let's take an example of a water flowing through a pipe. In this example, we can easily figure out that the mass going into the pipe would be equal to the mass of fluid coming out of the pipe. Now, from the conservation of mass, we get this integral equation, and if we try to shrink the control volume, we will get this differential equation as well. Because even after shrinking, the mass conservation has to hold, but the equation we have right now is in differential form. We won't go much into the details right now. That similarly, the conservation of momentum can also be converted into integral and differential forms. These mass conservation and momentum conservation equations together are called Navier-Stokes equations. As we can see that these two are highly coupled non-linear partial differential equations, and we can't solve one equation without using the other equation. This makes the analytical approach extremely difficult. This is why we have to resort to computational fluid dynamics. To solve these equations, we need something such as boundary layer condition. Boundary layer can be the ends of the body that we are looking at or the surface of the domain. NS equations are no set of ordinary equations. The mathematicians are still trying to prove that using these equations we can get a smooth solution. Now let's see how we use CFD in these scenarios. It involves three steps. First is the discretization, second comes solving, and then post-processing. Discretization is the most important step as it involves breaking down the body into very small pieces. As we have broken down our problem into small pieces, we can make linear equations for each and solve it accordingly. All these methods are to approximate the differential equations. The next step is solving. The computer solves these equations in steps that are called iterations. And if the meshing in discretization is done properly, the computer can solve these equations easily. After the solving, we have converged the solution. That is, we have come close to the solution. Now comes the final stage of CFD, the post-processing. In this process, we check the validity and accuracy of the solution that we have got. Simple steps such as checking if the solution is right by visual inspection or checking if the mass is conserved or not, and etc. etc. Now that I have briefed you with the topic, my friends are going to share its applications and talk about the dynamic principles in much more detail.
Now, after studying the introduction of computational fluid dynamics, now next we will be moving on to the next topic, which is application of computational fluid dynamics. Now, first application is in biomedical engineering. Computational fluid dynamics is widely used to solve complex problems in biomedical field. For example, CFD is becoming a key component in developing update designs and optimizations through computational simulations, resulting in lower operation cost with enhanced efficiency. Many simulations and clinic results have been used to study the analysis in biomedical applications, particularly in blood flow and nasal airflow. The case study of blood flow analysis includes the circumambulations of blood of ventricles, functions, coronary arteries, and heart valves. Meanwhile, the nasal airflow analysis consists of the following airflow in human nose: drug delivery improvement, and virtual surgery. Various applications of CFD in biomedical engineering are listed below. Now, next we will be moving on to the next slide, which is listed. These are the benefits of CFD listed below in biomedical field. First is blood flows through arteries and veins. Second, airflow in lungs, joint lubrication, cell fluid interface, tendon health, gas exchanger, artificial organ design, vocal tract analysis, perfusion in tissues, and life support system, last but not the least. Now next we will be moving on to the next slide, which is about application of CFD in mechanical engineering. How CFD is getting used in mechanical engineering field. First is heat exchanger. As heat exchanger, computational fluid dynamics has been employed for the following areas of study in various types of heat exchangers. For example, fluid flow maldistribution, fouling, pressure drop, and thermal analysis in the design and optimization phase. Second, fluid flow through pipe. Computational fluid dynamics is used to determine velocity and pressure of the fluid in a pipe and compare it with the result obtained in the laboratory, that is fluid flow module. It is also used to observe the heat transfer during the flow of fluids in a pipe and compare it with the result obtained in the laboratory, that is heat transfer module. Now next we will be moving on to the next slide. Uh, Combustion in IC engines. Computational fluid dynamics is used in the development of model of a spark ignition SI engine, that is, and the application of the engine model into an aggregated internal combustion engine. The development of model helps engineering students better understand the combined effect of chemical reactions, species transport, flow patterns, and temperature distributions in the SI engines, that is uh, spark ignition engines. Now, एरोडायनेमिक्स ऑफ एयरक्राफ्ट डेट फॉर एग्जांपल लिफ्ट एंड ड्रैग के लिए यूज़ होता है. ऑटोमोटिव फॉर यूज इन एक्सटर्नल फ्लो ओवर द बॉडी ऑफ अ व्हीकल और इंटरनल फ्लो थ्रू द इंजन, कंबस्शन इंजन, कूलिंग, turbo machines, and etc. All of these things are written over here in this slide, you can study. Now next we will be moving on to the next slide, which is about missile engineering. How CFD is used, computational fluid dynamics is getting used in the field of missile engineering. Due to the increased complexity of contemporary buildings and characterizing missile airframe, aerodynamics loads, force and moments, and the aerothermal environment is article aspect in the missile engineering. The aerodynamic information is used to access stability and control mission performance and movability. CFD is employed to supplement and extend test results of experiment approach. In addition, the flow visualization provided by CFD can be evaluated in all phases of wind tunnel testings, surface pressure distributions, wake line inflammations, and other visualization aids provides opportunities to observe the flow and its interaction with the various airflow components. CFD bridge added intelligence to critical design decisions during the wind tunnel testing phase. For example, envisaged components significantly assist in the scale model designs. Now, next topic my partner will be explaining to you, which is about Reynolds transport theorem and momentum equation. Thank you.
So let's make this and consider this this part as initial quantity of a fluid at time t, taking as 1, and after that at somewhat t plus delta t time it has moved over here. So this is t plus delta t, and this is second part. So so taking at time t is equal to 0. Suppose B be any property of fluid. So BCM T is equal to B at control mass at time t, same as B at control volume at time t. So this means that when time t is any specific, so these both coincide each other. So control mass is equal to control volume, taking it as a equation 1. So after some time, taking it as the control mass has moved from a delta t time in this part, so we write it as BCM T plus delta T, which is equal to BCM V plus delta T, can be taken as -1, -1 this part, plus 2 this part, which is equal to B control volume T plus delta T plus B N out at control C, taking as equation 2. So equation 2 minus 1 and dividing it by delta t. So we get this, and solving this we get delta t behaves like del t, and later on we get the formula this, and this is our Reynolds transport theorem.
The Navier-Stokes equation follows the principle of conservation of the energy, momentum, and mass of a fluid flow. In CFD stimulation, the Navier-Stokes energy equation provides the basic explanation of energy associated with the flow of behavior. Let us start by taking an example of fluid flowing through a pipe. One must analyze the mass, momentum, and energy associated with the flow. The simplification of this factor is the clue to understand flow flow of physics in different fluid systems. One way to easily do this with the help of Navier-Stokes equation. These are also governing equations in CFD. Navier-Stokes CFD analysis for both compressible and incompressible fluid. Navier-Stokes equations describe of the forces, all all of the motion that can act on a fluid. They are equation of motion for a fluid. It is based on simple concept, basically Newton's law of motion translated into fluid terms. So we will going to take an example of six-sided box of cube of fluid. So what are the possible force that can act on the surface of this fluid. Let us see. We will got direct pressure that can act on all sides, but we also have shear stress that can act on all sides. So, so let's add up all the forces, all the six sides, and now we have equation right here. As you can see the equation, now we have to add one extra force, R in instant intestinal fluid. We were just looking at forces on the surface of that fluid. There is one another force, other thing that can be act on fluid, which on body fluid. These are things that do not act on surface but actually act throughout the entire volume of fluid. These would things like gravity or magnetism, and them and then so coming to the final term, the essential idea behind Navier-Stokes is that forces equal mass times acceleration. So equation of motion is x direction is mass, time acceleration in the x direction is equal to force. In this in this r mass r density times r three-dimensional of r cube dx dy and dz, r acceleration in x direction. And on right hand side we have forces that are what are these forces? We got surface force and body force. After cancelling out on the both sides and substituting the terms with viscosity, and switching the vector notation, the final Navier-Stokes equations for full fluid motion just in the x direction is right here.
finite volume method on arbitrary grid. So we will understand what is finite volume method and how does it helps us in making our lives better and so on and so forth. So let's start. So let us first understand what actually is FVM, which stands for finite volume method. So as you can see, finite volume method is a method for discretizing or representing partial derivative equations in the form of algebraic equations. And how it is done? By dividing domains in finite size subdomains, which basically intact three properties. And the three properties are conservativeness, boundedness, and the last transportiveness. We will talk about all these properties in a bit. Until then, let us see what is the basic point of difference between finite volume method, finite element method, and finite difference method, and what is the need for finite volume method if we already have finite element method FEM and finite different method FDM with us. So the basic concept behind finite element method and finite difference method is given here. As you can see, the basic concept or the motto behind finite element method is that weighted residual method is used in order to reduce the errors, whereas in case of finite difference method, Taylor expansion theorem is used to identify derivatives or slope. So the problem with these two is that this method doesn't take into consideration the physics behind any problem or question. It doesn't matter that if the fluid is having transportive properties, it is additive, or and so on and so forth. Whereas in case of finite volume method, it is seriously taken into consideration as we discussed the three interacting properties earlier. So FVM is different from FDM and FEM in this way. Now let us see the step-by-step formulation for FVM. So the first and foremost step in the formulation of finite volume method is dividing domains into subdomains and then representing them through grid points. So as you can see in the diagram given here, the outer circumference or perimeter is our main domain in which we have divided finite spaces which we call as subdomains, or it can also be called control volume in case of FVM. And this same subdomains are known as elements in case of finite element method. And for making our life easy and making our calculations easy, we take centroids here in grid points. The next step, the second step in the step-by-step formulation of FVM is to integrate partial derivative equations or governing equations over each subdomain. And in this case, control volumes are the subdomains. The third step in step-by-step formulation is considering profile assumption for dependent variable and expressing them via Gaussian formulation. And the last step in this formulation is applying divergence theorem, which helps us convert volume integration into surface integration.